Thank you, Ken. There are no handouts, but I understand they have sent out for blankets. Try to stay warm here. As the field service, as the specialist that handles the mechanical things, a lot of the mechanical things for ESA, we get a lot of calls, and particularly related to pumps, although they're not pumps. A lot of the calls that I get relate to vertical turbine pump motors because they're tied in with the pump. And, excuse me a second. At one point, we actually put together a training class we have available. It's a one-day class where we cover all the mechanical aspects of both the vertical turbine pump and the attached motor, because when you put them together, you got a machine. It's kind of hard to do much with the pump without the motor, and vice versa. The two are they're a pair. The components, the pump bowl is the bottom part of the pump where the impellers and bowls are. That the bowl is what they refer to as the stationary part of the pump. I'll just mention, it's just in interest. If you take it's got 4 stages. If you take one of those, it's a pump bowl. If you take 2 of them, put them together, you still got a pump bowl. Put 4 of them together, you still got a pump bowl. That's the way the term is used. They use it for the individual stages, and they use it for the whole assembly. So you'll see that word pump bowl. The column obviously can be much longer, hundreds of feet in some cases. And then you got the discharge elbow up on the top and the motor that sits on top. So our focus today, let's stand it up so we can see it as it normally is. Our focus today is on the electric motor part of it. And if you're in this business of working on these vertical turbine pump motors and you don't know anything at all about the pump, you're at a disadvantage. Okay? So we'll try and educate it a little bit about what's going on with the pump and talk about the major issues that I have encountered with people calling me up and saying, hey, I had this problem, I had that problem with installing or running the motors. It's a little bit of an exercise in shoulda, coulda, woulda, okay? Because by the time they call me, there's a problem, and often the questions that I ask, well, this and this and this and this, and it's like, well, we should have, well, we could have, well, we would have. So this is an exercise we're doing today is going to kind of lay out those coulda, shoulda, wouldas, so that when you get to that point where there is a problem, you can go back and say, okay, I got this information and that information, we can solve this problem. Okay? How many folks in here work on the motors, vertical turbine pump motors? Almost everybody, I would guess. How many people here work on the pumps? Okay, great. And we got a good. If you have some field experiences that you want to share, put your hand up. We got a microphone, and we'll get the mic over to you. So let's make this participative, because it sounds like there's a lot more information out there than there is up here, and we can make this successful if we work together. Here's the areas that I've encountered as being problems when a vertical turbine pump motor is installed, and I get a phone call and say, there's an issue. The top one is vibration. Vibration is just a key issue with vertical turbine pumps and motors. So we're going to address some of those issues. High motor current. The motor's pulling high current. If you don't understand what the pump is doing and a little bit about pump curves, you're going to be at a real disadvantage, because if you worked on the motor, okay, and the pump isn't pumping right, the motor is the problem, right? If you worked on the pump and the motor's pulling high current, the problem is the pump, right? That's Murphy's rule for warranties on pumps. Another one is oil leaks. We don't run across this a lot, but it's enough that it's worth mentioning, and some of the issues that come up with oil leaks. The top bearings, the big thrust bearings, are usually oil lubricated, and when there's an oil leak, they can be tricky to track down. And bearing failures, problems with the bearings. The thrust bearings on the top of this are somewhat more sophisticated or complicated than on horizontal motors. So we'll address a few of those issues as well. Okay? Any of the 4 of these can result from problems on installation, or at least problems that should have been avoided before it was installed. And after it's installed and the problem is there, it makes it difficult to go back and troubleshoot. So we're going to try to address those. We'll start with the vibration issues. Obviously, the vibration issues on vertical turbines and pumps and their motors are most often related to natural frequencies and what we call resonance. A natural frequency is if I bump something and right now if I give this thing a little shake, I don't know if you can see this whole thing up here shaking. Okay, if I give it a little bump there. Okay, my computer screen is bouncing back and forth. I'm getting a little seasick from watching it after the third presentation. That's a natural frequency. Okay, if you bump something and it vibrates at some frequency, that's a natural frequency. That's determined by the stiffness, mass, and damping characteristics of the structure. Stiffness is if I push on this with 1 pound, how far does it move? Okay? So this is a little bit stiffer than this table. I push on this table, it's moving more than this is. This is stiffer than that is. Mass. This weighs more. This podium weighs more than this table does. Okay? So while its stiffness is greater, its mass is also greater. The table's stiffness is less, the mass is less. They could both have the same natural frequency because stiffness and mass work together to determine the natural frequency. Those are the two primary determining factors. Okay? You could imagine this pretty easily if you just took a ruler, use this for classes when I'm teaching vibration, stick a ruler out here and twack it and go wang, 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 wang. And we stick a piece of putty on the end of it, which adds mass, and we twang it again and it goes wah, 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 wah. Vibrates at a lower frequency because it has more mass. Okay? We can slide the ruler out so that it's softer and not so stiff and twang it, and that will also slow the frequency down. Okay? So that's natural frequency. Damping plays a factor. Damping is the ability of a structure to absorb vibratory energy. So if you hit something and it just sits there and rattles and rattles and rattles and rattles and rattles, there's not much damping. If you hit it and it kind of it's dead, okay, it has a lot of damping. Damping also affects the frequency at which something will vibrate, but not nearly as much as stiffness and damping. It has a minor effect on it, but it has a big effect on how severe vibration will be when you encounter resonance. The most common, probably the only resonance mode that you need to worry about with vertical turbine pumps and motors is what we call the reed frequency, which is when something is standing up or down and vibrates unrestrained on one end. That's different than being restrained on both ends, as is a horizontal rotor with a mass in the middle. It has a natural resonant frequency, but that's not a reed frequency. This standing up here and vibrating back and forth like a tuning fork is a reed frequency. The first means it's just bending back and forth. The second means that it's actually going into an S kind of a curve. Okay? This sounds like we're getting into some stuff that is a vibration tech should be involved in. We are. And if you're involved in vertical turbine pump motor repair, you will encounter this. So it's not like, oh, this is something that we don't need to worry about. You need to be concerned about this and have a fundamental understanding of it to be able to do a good job of working on vertical turbine pump motors and solving the problems that come up when you install them. You got another issue here, and that's that the motor sticks up and the pump sticks down. So you got at least two different potential reed frequencies, one on the motor, okay, and one on the pump. And when you install a new motor and it's vibrating, and a customer is saying, hey, I can't have that high vibration, it's something you did with the motor, the problem could be that the pump is down there going 10 times as much as the motor is, okay? And if you don't have any means of figuring that out, and you're going to chase this vibration problem up on the motor, but down below the pump is going 10 times, you're not going to solve the problem until you figure out that, hey, it's the pump, it's not the motor. Okay? So first and second bending modes, you got the motor, you got the pump. Then you've got this discharge elbow, which has a discharge that goes off in one direction, but perpendicular to it, you don't have a discharge. So the discharge provides additional stiffness to the structure. Got a pipe going off there, okay? Makes it stiffer. in the line with the discharge than it does perpendicular. That means it's going to have a different natural frequency in line with the discharge than you are perpendicular. So I've got the motor, I've got the pump, I've got first mode and second mode, first mode and second mode, I've got north-south, and I've got east-west. I've got 6, 7, 8 different possible frequencies that could be excited, okay, by this motor or by the machine, okay? When that happens, when there's some exciting force, usually rotating speed, but sometimes 2 times rotating speed, but most often 1 times, okay, you have what we call resonance. The natural frequency exists. It's there whether the machine is running or not. If the machine happens to operate at the same frequency that the structure likes to shake at, you've got resonance, and you can have very, very severe vibration. Okay? You don't have nearly this problem with horizontal machines. They're much stiffer. Horizontal machines have a structure which it is heavier duty, if you will, and if you push on it, it doesn't move as much. It's a lot stiffer than this motor sticking up here or this pump hanging down. They move pretty easy. They're not very stiff. Okay, so that lowers the natural frequency and brings it down pretty close to operating speeds. In fact, typical structural resonant frequencies for pumps fall in this range between 500 and 2,500 cycles per minute, which matches real close with rotating speeds of a lot of pumps. So we've got potential resonance at 2 different reed frequencies on the motor, 2 different reed frequencies on the pump, north-south, east-west, really close to operating speeds. Why don't we just put it on a variable frequency drive? And if you can't find a resonant frequency at a synchronous speed, put a VFD on it. You'll find it. It'll be there. It'll be just exactly the speed that the customer wants to run the pump at. Okay? So, for that reason, I say, if you're working on vertical pump motors, okay, and don't have anyone who's reasonably expert at vibration analysis, you're going to get yourself into trouble. There are going to be vibration problems, and you won't know how to solve them. Okay, so some of the things we'll talk about here, we'll give you some hints on what to do, things you can do ahead of time that will help you solve the problem when it does occur. But it requires a certain amount of knowledge about vibration and vibration analysis. Okay. Another problem we run across is you put the motor on, it pulls high current. Okay. And it doesn't make a difference what was done with the pump. If you fix the motor, and there's high current, the customer says it's a motor problem. They could have a pump in terrible condition. They could have put a new pump in and replaced it. They could have changed impellers. They could have changed the system, valve configurations, and done all sorts of things that could have caused high motor current. But unless you're expert enough or knowledgeable, and not expert, but knowledgeable enough in looking at the pump flow conditions and comparing it to the pump curve and saying, hey, if you've got this flow and you got this head, you're going to need that amount of power, and that motor ain't got it. It's not our problem. It's the problem is with the pump. If you don't have that, you're just at a loss. You have nothing to tell your customer. So we need to be able to understand a little bit about pump curves. Okay? Looks like I hit the button a couple times here. The pump curve describes how much power you need for the certain head and flow. Unlike electric motors, where you've got a certain amount of power and current and voltage, okay, on the pump, those are variables. You can have a pump with higher flow, or you can close a valve and bring the flow down. The head can go up, the head can go down, and the power required will vary as that head and flow change. So that's different than an electric motor, and it's described in what we call the pump curve. You also have a pump formula, which I think everybody working around pumps should know. This is the pump formula. Power, if you're in U.S. units of horsepower, flow is in gallons per minute, head is in feet, and head is analogous to pressure. It's how many, how high of a column of liquid that you have. Okay, but how high of a column of liquid you have, if you know what the density of the liquid is, it's going to have a certain pounds per square inch pressure at the bottom of it. So when I say head, we're just talking basically about pressure for a specific liquid. Okay? But the pump curve is in head. That's why we use head. The pump curve is in head. Okay? So flow times head divided by a number 3960 if you're using gallons per minute, feet, and horsepower, multiplied by the specific gravity, and multiplied by the efficiency of the pump. Let's simplify this a little bit. Anybody know what the specific gravity of water is? Thank you. 1. The specific gravity of water is 1. If I multiply by something by 1, I got something. I don't have to worry about it. I could take that specific gravity out if I'm dealing with water. Most of your vertical turbine pumps pump water. Okay? So let's take the specific gravity out. The little character on the end, the Greek eta, stands for efficiency. That's what engineers use when they don't want to write out the word efficiency. They use a little character. Well, let's suppose our pump were 100% efficient. We can deal with the efficiency later. Let's just suppose our pump was 100% efficient, and it was pumping water. Then I don't have to worry about either one of those two, and my formula gets to be simpler. Flow times head divided by 3960 is power. Okay? If you're an international and you're using kilowatts and cubic meters per hour and meters of head, the 3960 changes to a different number. But other than that, flow times head, adjusted by a constant just to take care of the units, equals power. It's that simple. Flow times head equals power. You should understand that. If you understand that and you know that your motor is pulling high current and you're pretty sure there's nothing wrong with the motor, guess where the problem really is? Got something wrong with your head and your flow, and you're pulling too much power. And if you recognize that and can look at the look at the pump curve, and talk to your customer about, well, what's the head and what's the flow? A lot of conversations stop right there, because if you ask your customer, you said motor's pulling high current. So, well, what's the head on the pump and what's the flow? Do you have a copy of the pump curve? My problem just ended, because he doesn't have the pump curve and he doesn't know the numbers. And I'm not being mean here to the gentleman, but that's the fact. I mean, if you don't know the head and you don't know the flow and you don't have a pump curve and the motor's pulling high current, it's not my problem yet. Okay? You have to get that information, and then we can work on why we have the high current. Okay? So we'll do a little thing here on pump curves, just so. And I've got a couple webinars available that you can download the recordings of them, where I've done presentations on how to read pump curves. So if you want to spend half an hour or so and really understand how to read pump curves, you go to one of those. This is just a real quick intro to give you a feel for what it is. This is a picture of not a pump curve, but a stylized pump curve. There's no units. The units along the bottom are flow, and typically that would be gallons per minute, or in international units, cubic meters per hour, acre feet per day. It's all kinds of flow rate units it could be in. We don't care. They're just numbers that represent the flow rate through the pump. Okay? Q, think of it as quantity, is in the pump formula. Okay? That Q stands for flow, the amount, quantity. Head is how much pressure is being pumped. Head is a way of measuring and how many feet of liquid, how high of a column of liquid could you pump at that particular pressure, and that's the vertical axis. That's the vertical axis. So I've got flow and I've got head, okay? I've got flow and I've got head in the equation. I've got flow and I've got head on the pump curve on the chart. And that describes all the possible heads and flows that pump can do. I can have a lot of flow out here, 2,500 gallons per minute and only 50 feet ahead, or I could deadhead it and shut it off, close it down completely, and I'd get 250 feet ahead. Anywhere in between the two is where that pump can operate. Okay? So, in addition to that, I've also got efficiency. Efficiency is the green curve, 0 to 100% efficient. Here's the efficiency in the pump formula. Okay? And this green line is the efficiency versus flow. If I've got that discharge closed down and I'm not pumping anything at all, I'm putting energy in and I'm getting nothing out, what's my efficiency? 0. Nothing's coming out. I'm not doing any work. I'm putting energy in. As I open up the discharge valve, the efficiency goes up. It gets to a best efficiency point. A best efficiency point. I don't know if I can catch that. Let's see if I can catch it up there. This is a game I play. Ha! I got it. Okay? I got it right. That's the best efficiency point. And then from there, if I open up the valve some more and let some more liquid go out, notice the efficiency starts falling off. You get more flow, you get less head, but the efficiency is dropping. That's where everything in the pump is happy, right at that best efficiency point. That's where you'd like the pump to run. Okay? And then I've got power. The formula up here says, hey, if I have flow and I have head and I have efficiency, I can multiply this whole side out and I can get power. Right? So for any point on the curve, I got head, I got flow, I got efficiency, I have power. I got a power curve down here. Okay? Interesting thing about the power curve. You'll notice that as the flow goes up, as the flow goes up, the power goes up. Okay? This was an interesting experience for some plant mechanics working on a pump. Installed a new pump, started it up, checking the motor current, everything looks fine. He says, okay, let's load this thing up. Okay? I want to see what it does when it really gets, working hard. And he closes down the discharge valve. And the pump starts going and starts making noise, and they're really loading it up. And what happened to his amp meter? It went down. Looks at that, wait a minute. I just closed the discharge valve. That pump's really working hard now. How come my current went down? Because when you closed the valve, the flow went down. Okay? So this is true for centrifugal pumps. It tends not to be true for axial flow pumps. They look more like a boat propeller than like a centrifugal impeller. It tends to be the other way. Vertical turbine pumps tend to have what we call a mixed flow impeller, which is somewhere between a centrifugal and an axial flow. So while this pump curve and a lot of pump curve, this pump curve and a lot of pump curves illustrate higher flow equals higher load, on vertical turbine pumps that may or may not be true. Okay? You got to look at the pump curve and see where it is. And that curve will be on any pump curve that you've got, there will be one that represents the power. And that'll tell you how much power that pump needs at any given flow and head. Okay? So, nice little recorded webinar. If you want to know more about reading pump curves, download one of those from the ESA website and learn all about them. Does anybody have questions about them just in general? Kind of makes sense what's up there? Okay. All right. That's important because you're going to get that call from the customer that says, hey, your motor's pulling high current. Just repaired it. Send it into you. Send it back. And this is where you have to go. This is your first question when it says high current on the motor. What's the head? What's the flow? Going to get a copy of the pump curve. Okay? All right. Let's see. So that was the pump curve and the pump formula. Another factor that affects the load on the motor is the lift adjustment on some vertical turbine pumps. It makes a difference if that impeller is a closed impeller or a semi-open impeller or an axial flow impeller. And we'll show you some pictures of those. Okay? A closed impeller has a suction eye. The suction eye matches up with a wear ring in the stationary part of the pump, in the pump casing. Okay? The open impeller does not have that, and as this impeller is lifted up, part of the lift adjustment will lift where that impeller is running in relationship to the stationary element of the pump. It opens up the clearance between the face of the vanes and the wear plate that's next to them. So you can see if I raise or lower this impeller 50 thousandths, it's going to have a much bigger effect than if I raise or lower this impeller 50 thousandths. So some of you may be aware, or had heard, that, hey, if the motor pulls high current, I can lift the pump shaft up some and take some of the load off the motor. How many people have heard that? Okay, not very many. But you'll hear that. People know that. People in the pumping industry know that. Got to be that kind of an impeller. If it's this kind of an impeller, it won't work. Okay? So my point there was to dispel the notion that might have been out there that all you have to do is raise the pump shaft to take the load off the motor. And I don't have to dispel that notion because you didn't have it. That's okay. Now you know about it. And we'll cover the issue of setting that pump shaft lift here in a minute. Another issue that happens is oil leaks. How many people incurred oil leaks on vertical turbine pumps? They happen. You've got that big oil reservoir up there on the top. Just to explain what's going on, this is wrong button. There we go. This is a pump housing on the top of the motor. I'm sorry, pump housing. Bearing housing on the top of the motor. Okay? Got a pair of angular contact bearings in there. And this is filled with oil to some level. Usually the oil level is right about the middle of the lowest ball. Okay, lowest roller level. So oil level is about through there. Okay? When a pump is running, this lower bearing will pick that oil up and pump it, literally pump it, up into, that's an inconvenient location for that button, and pump it up into the upper bearing where it comes out and starts circulating around. So oil levels will be up as high as here in the bearing itself. Okay? To keep that oil from running down inside the motor, there's something called a stand tube, and the stand tube will be right in there. This picture should help clarify that. Okay? This is the carrier that has the bearing on it. It's turning. This is turning. Okay? Right inside of here is the stand tube. So the stand tube is inside of the carrier which is spinning. Okay? And the pump shaft is inside of the stand tube. So the stand tube is stationary, this is turning inside, and that is turning outside. So you got a situation like this. Okay? And it's filled with oil up when it's running up pretty close to the top. If the oil can make its way over the top, if any oil can make its way over the top and start running down the inside, it'll have a capillary action and it'll keep pulling more oil over with it. So you got to stop it from ever getting started at that. Okay? In the seminars that we teach on motor repair, either the AC motor repair or the one that we do for vertical turbine pumps and motors, we talk extensively about things that you can do when you repair the motor to prevent that leak. Okay? We're not going to do that today. That's more into repair. Here we're talking about installation, but just so that you understand what the problem is. Another potential way that oil can leak is it can be pulled out the top up here and usually leaking to the outside if there's an airflow or air pressure imbalance. Okay? If the oil chamber has a different pressure than the atmospheric pressure, so you're getting airflow through there, it'll pick the oil up and it'll take the oil out, so there's another place that you can get oil leaks. Okay? The bearing arrangements are a concern. This will usually show up when you install the machine. And it can show up as a bearing failure, it can show up as bearing noise, it can show up as high temperature. There's a lot of different configurations of that thrust bearing on the top of the motor. It could be a single angular contact ball bearing, simplest configuration. It could be a pair or more, 2, 3, sometimes as many as 4 different bearings at the top. And they can be configured different ways, some for up thrust, some for down thrust, face to face, back to back. There are spherical roller bearings that can be mounted on springs. Okay? In addition to the spherical roller bearing, sometimes you'll have the spherical roller bearing along with a ball bearing, where the spherical roller bearing takes the axial thrust and the ball bearing maintains the radial concentricity. Okay? There's a thing called a pump pack bearing, where you got 2 down and 1 up with different angles, different contact angles. Some of them have the why did that name jump out of my head? Pardon? Kingsbury. God, how could I forget that? Kingsbury thrust bearing that has tilting plates and a solid rotor that turns to support the weight. So a lot of different possible ways the bearings can be configured. If the motor was taken off of the pump and sent in for repair, and the person who did the disassembly very carefully noted the configuration of the bearings, and they're certain that they were put back in the same way, and that motor went back onto the same pump, you probably won't have any problems. But I think I used the word if. I thought I used that word, okay? If the motor goes back on the same pump, many customers will swap motors around, okay? And different pumps may be configured differently. They may be very similar pumps, and the same motor would fit on two different pumps, so they got one spare for the two. But this one's pumping one application, and that one's pumping a little different application, and the head and flow characteristics are different. And this one's a different depth, and it has different axial thrust than that one. And they don't tell you that they switched the motor from one application to another. They just tell you the bearing's now running hot. And the bearings should have been configured differently. These vertical motors sometimes are configured at the factory for one application and have been moved to some other application, bought, sold, or whatever, just because it is the same frame size, horsepower, speed, and it's got two bearings in it, doesn't mean that it's configured for another application. In one application, that might be one bearing up and one down because it's subject to upthrust. In another application, that could be two bearings both down because it's a very deep well pump and it has a much higher axial load, and they don't worry about upthrust, but they got to be able to hold that shaft. Okay? Same motor can be configured lots of different ways for different applications. Okay? So you want to confirm the application, and if you want to know more about it, we have a seminar, a one-day seminar we do on vertical pump and motor applications where we cover it extensively. Principles of medium and large AC motors covers it, and mechanical repair fundamentals covers it. Those are 3 ESA resources available for more information on bearing configurations. Okay? We mentioned it here because where does the problem come up? It's installed, bearing's running hot, bearing is noisy, got some other problem related, bearing failed. Okay. When you're trying to decide which way these bearings go in, tandem, back to back, face to face, some of the hints that you get are in the housing and the shaft with the way that the bearing is retained on the shaft and the way it's retained in the housing. Don't have time to go into it right here today, but in those seminars we cover that. So somebody says, God, is this thing supposed to have one up and one down, or is this the one that's why they both go down? If you take a look at the way the shaft is configured and the housing is configured, there'll be hints about that. Doesn't always tell you what's right, but sometimes it'll tell you that it can't possibly be this one. Okay? If there's nothing holding the bearings down into the housing, you can't have bearing configured for upthrust because there's nothing to hold the bearings. Okay? So the point is there's some hints there about that. The pump manufacturer, when a pump was designed, provided some sort of a axial load specification that those bearings in the initial motor were designed to hold. Okay, so if you're switching motors back and forth, or your customer is switching motors back and forth, somebody needs to do this calculation of the load for those particular bearings. And if you check with your bearing supplier or just look it up in the catalog, there is a dynamic load rating for all vertical bearings. And there's some calculations that need to be done to come up with it. They're not simplistic. They're not particularly complicated, but don't think you're just going to read a number off the table and not have to do any multiplying or dividing. There's some factors that need to be applied to come up with the load rating for that particular bearing. And then you have to know what the load is from the pump. Okay? So if you're working on vertical pump motors and you have no knowledge of this, if this is something like the first time I've ever seen this, be aware that this is one of the areas that you can get into trouble when a motor goes back and the customer installs it, if you don't have any knowledge at all about what that vertical load rating is for the bearings in their present configuration. Okay. Has the motor application been changed? That's one of the first questions you ask the customer if you've got problems with bearings. Did that the same pump that the motor came off of? We got a bunch of the pumps are all the same. Oh, no, they're probably not all the same, and that could be where your issue is. All right. You can do a lot to help yourself if you will test run the motor properly in a service center before it goes out. I would guess that most people do that. There are some tests that can be done there that will help when it gets out on the job and there's a problem, particularly for vibration. This is a test bed, and notice it's got a hole provided, so if I have a solid shaft vertical motor, I can bolt that thing down and test run it. Okay. There's other ways of test running solid shaft motors with the shaft out the bottom. I've seen people set it up on blocks of wood. That's not necessarily bad. It's got some potential problems. Durometer pads work pretty good. If you're not familiar with durometer pads, they're a soft pad which compresses from the weight of the machine and isolates it so that it is basically floating. If you set the vertical motor up on blocks of wood or on durometer pads, it's a good idea to start that machine on reduced voltage. If you start it on full voltage, the torque can cause it to spin, cause the stator to spin, and give you some problems that you don't want to encounter. So some thoughts there. If you bolt the motor down, you can do a bump test on it. How many people know what a bump test is? Okay, not everybody. If you're working on vertical machines, a bump test is something, when somebody says that, you should automatically know what that is. You should have done it or have a technician who has done it. And it wouldn't hurt, if you've got a technician that's doing it for you, to have him show you what one of them is. So if you talk to your customer about a bump test, the customer looking, what the heck's a bump test? That doesn't sound like anything technical. And you should know what it is. Okay? Fundamentally, you put a vibration transducer on the machine that can measure frequency of vibration and amplitude of vibration, and you take a mallet or a block of wood or a rubber mallet and you wall up the machine in the same direction the transducer is mounted, and you let it vibrate. And you measure that frequency of vibration and you determine its natural frequency. Okay? These vertical motors, most of them, any large one of significance, come from the manufacturer with a known read frequency. The read frequency is what frequency it vibrates at when it's bolted down. So that's the motor read frequency. That is not the frequency of that motor installed on the pump. When it's installed on the pump, it'll have a completely different frequency. So there's confusion sometimes. The motor manufacturer says the read natural frequency is 4,000 cycles per minute, and it's a 1,800 RPM motor. I shouldn't have any problem. That's not true. That's the motor bolted solid on a test bed. You take that same motor and you bolt it on top of a pump. It has a completely different and much lower natural frequency. Okay, so you can test the bump. You can do a bump test on it right here. It's such a simple thing to do. It probably takes 15 minutes to do a bump test, and you can document that. And if a question ever comes up about it, you've got that in your documentation, what that is, and you can check it with the manufacturer, see if it matches what the manufacturer says it should be, and understand that it has nothing to do with what you're encountering on site, because what you're encountering on site is an installed read frequency of the motor on a pump. Okay? All right. Verify proper running condition in the service center. Make sure that the bearings are proper to handle the load. When you're testing it. And there's two different conditions that can happen here. Excuse me. If you've got for instance, a spherical roller bearing in the top or a pair of angular contact ball bearings, those are made to take the load from the pump. I'm guessing that everyone knows at this point that the pump rotor hangs on the motor. Okay? So when it's installed, it's got a pump rotor hanging on the motor. So you got that load in addition to the weight of the electric motor rotor itself. When you're test running in a service center, you don't have that weight on that shaft. And if you've got multiple angular contact ball bearings or a spherical roller bearing, you don't have the minimum load necessary for running that bearing. And you want to limit the time that you run that bearing to at least not more than a couple of minutes. Okay? Unless you can find some way to artificially put some load on it. Okay? You know about not running horizontal machines with a roller bearing on the drive end without any load on it because the rollers will skip. You have the same problem with a vertical machine if you don't have sufficient load, vertical load. Okay? So that's a concern. Spherical roller bearings and multiple angular contact ball bearings, make sure that you have at least enough weight in the rotor to meet their minimum load. Where do you get that? Look it up in the bearing catalog or call your bearing vendor and ask them what's the minimum load for that particular axial load for that bearing. They should be able to provide you with that. The second issue comes when you have a spherical roller bearing with springs installed in it. And the springs, in some cases, the springs are there so that if there's upthrust and the electric motor rotor comes up, the pump is lifting the rotor in some conditions, the bearing would unload, and then when it reloaded, the rotor would crash down and impact the races together and the rollers in the bearing, because a spherical roller bearing has no control. Once you lift it up, it's loose, and then it bangs back down. So to prevent that from happening, the lower race of the bearing is mounted on springs. How many people have seen that? Okay? And that the springs will lift that outer race and maintain contact between the balls and the races when it comes up and down so that they don't smash into each other. Okay? But those springs can be so strong for a very deep pump that they would overload the guide bearing on the bottom, because with no pump on there, those springs are going to lift the bearing up in the housing until the guide bearing on the bottom hits the end, that 5 to 10 thousandths end play you put in there, going to lift it up, and that lower guide bearing is taking all the thrust from those springs. And you can calculate the spring tension. Now, you can measure the spring tension pretty easily. Just set it on a scale and push down and compress it as much to the height that it'll be compressed when it's installed, and see how many pounds of force it is, multiply by the number of springs, and you know how much force you've got. Then you can look at the maximum axial load on that guide bearing and be sure that you're not exceeding it. Okay? So that's a concern. One of the concerns that come up for test running the motor in the service center. Or on site, if they put that motor on site and they run it, and maybe they're doing the installation, you're not doing the installation, and they don't know about that, and they just go and run the motor for 20, 30 minutes or an hour or a day. Okay? And they ruin the lower bearing. Okay? You wouldn't know that. Never run the motor without proper oil. You can't squirt some oil on the bearing and run it. People have tried that. They've bought new bearings. Okay? The static oil level should be about the middle of the lowest ball if there are multiple bearings. And once that starts running, it will pump the oil up through the others. Okay? But it needs to be well below the top of the stand tube. You can't take those measurements when the machine is assembled. You would have to take those measurements when the disassembled. Where's the top of the stand tube compared to the bearing when it's the lowest ball in the bearing? Okay, when it's not running. Okay, so verify that. When the machine's running a service center, this is probably one of the most important things. You want to record the vibration. You want to take vibration spectra. Put your transducer on it and take a spectrum. Horizontal. That on a machine, if it's horizontal, you take a horizontal reading, a vertical, and an axial. On a vertical machine, they're all horizontal. We usually refer to those as radial. Okay? So you might take radial in line with the junction box and radial at 90 degrees to the junction box. Okay? The vertical reading is pretty useless. It's not really necessary to take it. It doesn't hurt if you do. Okay? But record a vibration spectrum. That proves to you and to your customer that machine runs smooth when it's properly bolted down on a test bed. And it goes out on the job site, and all of a sudden you have high vibration. You say, well, what was it when you test ran it? Well, we didn't check it. It's not going to cut it. You say, here's the spectrum. This is what it ran. We measured this. It ran fine in the service center. Okay? And you may also want to take some high-frequency vibration readings, which are related to bearing. If your vibration analyzer has HFD, spike energy, peak view, shock pulse, anything like those that measure in the high-frequency range, it's good to record that data as well. Just good documentation procedures. Okay? That's good. You did all that, right? Yep. You pulled it. No, yeah, we talked about all that. Great. Transport and storage, never lay down a vertical motor. Okay, the thrust bearings are not designed to handle that lack of vertical load at all, zero vertical load laying down. So don't do that. Don't do that. Okay, can't get much more clear than that. The other reason is the oil. If there's any oil left, it'll start leaking and start to run out, and you can create oil problems that way. When you store it, some of the vertical motors have a different oil level marked on the sight glass for storage, and it'll be higher if they raise the oil level up to completely submerge the bearings so there's no air there to avoid corrosion to the bearings. If they're completely submerged in the oil, they're protected. Okay? And then you got to drain that oil back out before you start the motor and operate it. If this is for storage versus operation, not all the technicians at the customer's facilities are aware of that, and they just fill it up to the highest level marked on the sight glass without seeing it says storage level or anything like that, and they run the motor and they got all kinds of oil leak issues. Okay. All right. Plan your work. Work your plan. When you're going out to the job site, if you do things in a proper order, this is the whole point of the whole presentation. If you do things in proper order, you'll eliminate a lot of potential problems. Okay? The flange runout on the motor is something that should have been verified in the service center. So when you get out to the job site, alignment's going to be an issue, and we're going to talk about some of those alignment issues. You should know what the runout was on the flange, both radially and for face runout as well, perpendicularity. Okay. If you can't verify that, and you're at the job site and installing a motor, maybe it's one that the customer's had in storage, and there's no data on it, then you need to take that motor and raise it up and get under it with a dial test indicator and indicate that flange and find out what your runout is. Excessive runout will lead to alignment issues. Determine the clearance between the ID or OD of the motor flange and the ID and OD rabbit on the pump housing. Okay? So you do that with a micrometer or some measurement tool that will give you those dimensions. And you want to know what the clearance is. That clearance will determine the amount of horizontal alignment latitude that you have. Okay, so when it's already set on there, it's going to be too late. You can get it that way. Well, it won't be too late. You can set it on there. And actually move it side to side and measure it that way. Also, if you don't have a big enough micrometer. But usually, what you want to do is you want to know what those diameters are and measure the difference between them. So next thing is to mount and perform a bump test. This is the motor sitting on the pump. You did the bump test when I had it bolted down on the test stand. This is much more important than that. You have to do this bump test. You have to know what the natural frequency of this machine is, and if it's anywhere near rotating speed. And it will be different in line with the discharge than it will be perpendicular to the discharge. So you need to do a bump test in line and a bump test perpendicular. Whether you align the motor at this point or not, some people like to run the motor before they align it. That one can be moved around where you do the alignment. Okay, but before you run the motor, jump down to this one. Before you run the motor, you've got your vibration instrument out there, and your vibration instrument has a reference pulse pickup that will see a piece of reflective tape on a shaft or a keyway on the shaft or something sent out a 1 pulse. It's really difficult to get those set up once the machine is running. You can't stick a piece of tape to the shaft, okay? So you want to get that done before you start the machine. Because if you've got that reference pulse pickup on there, you can do what are called Bode plots that will pinpoint what the natural frequencies are during a coast up and start down, but you can't do that without the reference pulse pickup on there. And you've got to start the machine to check rotation and test run it anyway. So the point is, if you just take that extra second to stick that reflective tape on there for your instrument, then you'll be able to track speed and do some really nice documentation of natural frequencies. If you start the machine up and it's running and you don't have the tape on there, you can't do that. And then you got to shut it back down and restart it. So save yourself some trouble and put that tape on there first. Okay? Let's see. Check proper rotation. I'm going to show you some pictures on that. Before you couple it to the pump, you do not want to start a motor in reverse direction as coupled to the pump. I'll show you some pictures on that. So you're going to check rotation. You're going to start and run the motor. You might as well have that phototach on there before you do it. Then you record your vibration data, including Bode plots during the coast down. A Bode plot during a coast down takes amplitude and phase again and again and again and again and again and again and again as it coasts down and coasts down and coasts down. One of the characteristics of resonance is that the amplitude peaks and then goes back down, and the phase angle shifts 180 degrees. Okay? You can't get that phase angle shift measurement without the phototach. Your instrument can't measure phase without having that phototach. So that's got to be on there. Okay? Let's see. Then you attach it to the pump shaft and you set the lift. We'll talk about that. If you have a mechanical seal on the pump, okay, when you're setting the lift adjustment, you're moving the shaft up and down, you can't have your mechanical seal locked in. That seal's got to be loose. When you're doing the alignment, you may be moving the shaft, side to side or things. That seal's got to be protected so you don't damage that seal. If you got packing, it's no problem. Okay? Then you operate the pump, you verify the load on the motor, and you check in the head and the flow on the pump, and you make sure that everything matches up on the pump curve. Okay. So let's look at some details related to that series of things. First, anybody have questions? Because we're going to see some more details on some of those. Okay? These are the NEMA tolerances for flange runout. Size of the flange, the dimensional tolerances, so up to 3 thousandths over, 5 thousandths, up to 10 thousandths over. That's the amount that it can be, that the ID of the flange or OD of the flange is larger than the spec. And this is the face runout and the eccentricity. Okay? So there's tolerances for those that you should at least meet the NEMA standards. Okay? And you want to know how that matches up against the pump flange. Here's the thing. When you go to do the alignment, if you're within tolerance here, you don't have an alignment problem. Okay? Unless those tolerances aren't the same on the pump. Pump manufacturers do not have tolerances for runout. An individual pump manufacturer might, but the Hydraulic Institute does not provide those. There's nothing across industry as we have for NEMA for the motor. The second problem is most of these vertical turbine pumps, almost all of them, the pump rotor hangs on the motor. So until the motor is on and the coupling is on, the impellers are sitting on the housing and you can't turn the shaft. So how do you check the runout on the pump flange? It's really a problem. I don't have a real good solution for that. I can tell you what some folks have done, but it's not a universal solution. Okay? So this bottom one, is there any way to verify that? In some cases, yes. Some customers are pretty high tech, and when they had that pump repaired, that's one of the tests that they have done, and they've got documentation that shows what the runout is, and they maintain tolerances. Some other folks, they don't know what you're talking about. That's the way it came from the manufacturer. It must be right. Okay, the bump test, inline and perpendicular to the discharge. This is the time you do it after the motor is bolted on. You can do it before or after you run it. I like to do it before. Then I know what I'm looking for when I see my Bode plot with my coast down. I know where I'm going to encounter them, and I'm just verifying it with the Bode plot. But you can do it after as well. Okay. Usually you mount the transducer up near the top on some solid component, not on the fan cover, not on a shroud or something. And you bump the motor on the opposite side with a mallet or a block of wood. Don't use a sledgehammer or anything hard. Don't use a dead blow hammer. You want, when you strike it, you want the hammer to bounce off. So a dead blow hammer would stick to the part. So something that's got a soft enough face that you can bounce it off of there, and it'll sit there and vibrate, and you're going to get a real nice spectrum on your spectrum analyzer. Okay? Record the spectrum. If some of the spectrum analyzers have a special setup for a bump test, and if you check on your documentation or check with your vendor that sold you your vibration analyzer, hey, do you have a setup in here for a bump test? And they'll say yeah or no. Or if they say no, start with 200 lines, 400 hertz, and just bump the machine continuously while it takes the spectrum. So you're bumping and you're bumping and you're bumping and you're bumping, and you push the button on your analyzer and it takes the spectrum, and then you stop. Okay? You'll get a pretty good indication that way. If it's got a special setup, it may have a trigger to where it can tell when you bumped it. They may have they may use different types of averaging, okay, in your spectrum analyzer. If the peak that shows up is pretty close to operating speed, you know right away you're going to have a problem, okay? Generally, you want the operating speed to be about 15% away from the natural frequency, okay? If it's not, put it on a VFD. You can get it there. Right on it. I have a friend of mine, I have a lot of friends of mine who do vibration analysis for a living, and one of them told me the Chinese word for VFD is ka-ching, as in the cash register. Okay, resonance problems, it's not a simple task. If you got a vibration tech who does a pretty good job of balancing and just does general vibration analysis and stuff, he's got a level 1, he's been to a class, he may not be the person to really analyze a natural frequency problem and look at structural vibration. Usually that's something that you're, level 3 tech or above. They probably know something about modal analysis. They may have never done one, but they understand what modal analysis is. They understand the different modes that something can move in, translational, rotational, etc. In the 3 different planes. There's six standard vibration modes. If they know that, if you ask them those questions and they knew those answers, they do a pretty good job of it. If they said, what's a mode? That's not the person to be trying to solve a structural resonance problem. Okay? So we already talked about that. First and second bending modes in the pump and in the motor, in line with the discharge versus perpendicular to the discharge, and then put it on a VFD. Okay? If you want some more information on vibration analysis, these are some great resources that ESA has available. There's a 12-part series, Vibration Analysis for Service Centers. It's 12 webinars that I did about 3 years ago. You can buy the recordings, and there's a booklet that goes with it as well. So if you're looking for a source to get some just basic information on, all I want to do is fix the motor. I don't want to get into all this vibration analysis stuff. But it looks like I got to. This is a good place to start. Okay, test running the motor uncoupled. You've already mounted your reference pulse pickup. Are we over time already? Are we supposed to be done at 5? Wow, I'm sorry. I'm running late. Okay? This is important. You run the motor uncoupled. You're going to check direction of rotation. You want to do this start up and coast down. Okay? So you run the motor uncoupled, and then you couple the pump up, and then it vibrates. The problem's not the motor. Okay? Does that make sense? Sometimes that's hard to get across to a customer. Or you didn't run the motor without it being coupled to the pump. They just hooked everything up and tested around, and now it vibrates, must be the motor. No, we run the motor first, and it runs smooth, and there's no problems. Then you hook the pump up, and then it vibrates. The problem's not the motor. Okay? Then we can start looking for the real problem and start arguing over whether or not I'm going to pay for it. Okay? All right. Do not start the motor coupled to the pump unless you know it's running the right direction. I can't think of any clearer lesson than to take a look at those pictures. Okay? That crack is not supposed to be there. They started, the couplings are threaded. If you start it the wrong way, the couplings unthread and the shaft comes up, and this is what happens. Okay? This is why you always check the direction rotation before coupling the pump. Okay? Shaft alignment is a problem. The motor flange, you know it's true. You check that. No problem. You don't know what the pump flange is that's mating. It could be eccentric. It could be out of square. There's no way to test it. There's no easy answer to this. Okay? What some folks have done, some folks have a procedure when the pump is out, they verify that and they measure it. Some particularly in the petrochem industry, they take the pump housing and where the seal mounts, okay, that in that housing, they have machined a surface on it, true with the bearings. Okay, so they took that pump housing that had a bearing in it, and they put it in the lathe, and they trued it up to the bearing bore, and they machined a surface on the outside of it. And then when they assemble it, then they've got a reference surface, so they can come down from the motor shaft and dial indicate or laser indicate to that and tell if there's any run out. And they've done that ahead of time. You can't hardly do that after the fact. The pump rotor is sitting down in the pump, and until you lift it up on the pump shaft, you can't make the measurements. And you can't make the measurements unless the motor's sitting on the flange. With the motor sitting on the flange, you can't make the measurements. So it's just one of those can't do it things. So that's a problem. You can indicate with dial indicators, and you can do it with laser systems. And there's ways to do it. We're not going to get into a discussion of doing alignment. There will be a vertical shaft alignment standard out. If you didn't know it, there is now a shaft alignment standard for horizontal machines, an ANSI ASA standard. And there will be a vertical one out here hopefully in a few months. It's out for voting. I worked on a committee on it. So if you want more information about it, I was hoping we'd have it by now and I could direct you to it, but just have to wait. Next year I'll tell you what it is. Okay? But it's coming out. Okay, protect the mechanical seal. Let's see what else is important here. If you want to adjust the offset, when you're doing alignment, here's your two shafts. You want to adjust the offset, you got to have clearance between the rabbet. If the rabbet sits solid, you can't do that. Okay? And if it's off really severely, that means sometimes you got to go in, take the motor off, and do some machine work, or go to work with a hand file to give yourself some room to move that motor to get that horizontal alignment correct. Okay? As far as angularity, okay, the horizontal alignment is much more important than the angularity. Okay? I can put shims under bolts, and I can get those shafts exactly parallel. But if they're off like this, that's a bad situation. Okay? But if they're pointing right at each other and at a little bit of an angle, that's not nearly, this is not as bad as this. So the horizontal alignment is more important than the angularity alignment. And I'll leave it at that without getting into too much more in terms of alignment. But aligning a motor and a pump, it's not an easy task, and it's not the sort of thing that you can just write a procedure for it, because there's too many different situations, and sometimes there's just no place to mount the indicators. Okay? Setting the pump lift, get through this here pretty quick. You got to lift that pump shaft up. Two ways it's done. Hollow shaft, there's a nut up on the top. Really simple. You just tighten the nut up and lift it up. If it's a solid shaft, the coupling has some provisions in it. Some of them have threaded fittings where you thread the couplings together or apart to raise or lower the shaft. Some of them have spacers that need to be put in. These are pretty complicated little devices. You have to completely understand how they work. Okay? If your impeller is enclosed, the lift adjustment is not critical. You just don't want it rubbing. You don't want it rubbing on the top. You don't want it rubbing on the bottom. If it's a semi-open impeller, you're going to adjust the load when you adjust that clearance. And you'll also be affecting the efficiency of the pump. Okay? So the type of the impeller makes a difference. Just to cut this short, you want to know what the maximum amount of clearance you have. Sometimes that means just raising the shaft up until you can rub on the top. And, of course, you know where it was on the bottom. Then you know the full range that you've got. If it's a enclosed impeller with a suction eye, you want to be someplace in between. If it's an open impeller, you got a few thousandths of an inch underneath here. And to make that determination, you need that information from the pump manufacturer. Here are some numbers for lane pumps for an enclosed impeller. So they're not critical. They're not critical. So 6 inches, 1/16 of an inch, or 1/8, or 3/16 or 1/4. Depends on the size of the pump. Those are nominal numbers, and you only have to get close to them because it's got a suction eye. Just don't want it rubbing. When you get to a semi-open impeller, here's the specs for national pumps. They want 15 thousandths clearance plus 5 thousandths clearance for every 100 feet of pump head plus 5 thousandths of an inch for every 20 foot of pump depth. So this is what Lane specifies for their pumps for setting the lift. So I've got a 500 feet of head and a 20-foot deep pump. I need 15 plus 5 times 5 plus 5 times 2 equals 50. My clearance, my lift is 50 thousandths. I've got to raise it up 50 thousandths. So an open impeller, you're talking in thousandths of an inch. A closed impeller, you're talking in 1/16 of an inch. Okay? All right. The other things that are critical, once you get it running, you want to record all the electrical data. You want to know your voltage and current on all 3 legs. If an overload occurs and it's a semi-open impeller, you could raise that shaft up a little bit. That'll change the efficiency of the pump. They won't get as much fluid out of the pump as they would normally, but if it's overloading the motor, that may be what's necessary. You want to record the speed, current, voltage profile. So if they're going to change it, they're going to be run through a series of different loads on this pump, open and closing it. You want to know what the voltage was, what the current was, and what the rotor speed was. And you want to document that. Come back later, and you think you got an open rotor in the motor. You can check to see if your speed, current profile, voltage profile has changed, which would be a key indication of rotor problems. Okay? And you can use your vibration analyzer as a tachometer, usually. All right. Starting the pump. Yep, we did all that. Take vibration spectrum with it running. We recommend 400 lines, 400 hertz, 404 averages as a typical setup. That's probably what your vibration guy does anyway. If you've got that capability, record your high frequency readings for bearings. And if it's variable speed drive, you want to run it through the speed range, and you should already know where your natural frequencies are, and make sure that VFD is programmed not to let it run at those natural frequencies. Okay. High 1x vibration. Where can that come from? You know, the motor ran perfectly smooth in a service center. We installed it on the job, and it's got high 1 times. It's not running close to a natural frequency. We knew what the natural frequencies were. We've eliminated the possibility of resonance. Why is it running with high 1 times? You got a head shaft that goes through on a hollow shaft. You got a head shaft that goes through the pump shaft. There's no guarantee it's in the middle. That's a rifle bored shaft, motor shaft, and that bore is not 100%, true. that pump shaft can be off to one side or another and throwing it off a little bit, creating some imbalance. You could have coupling issues, okay? Coupling hub run out, either on the top or on the bottom. On the top if it's hollow shaft, on the bottom if it's solid shaft. Or you could have issues with the pump shaft. Whoops, wrong button. Wrong button. There we go. The pump, the high vibration could be coming from the pump. None of these are abnormal. These are all what you would consider normal conditions. And if you have high 1 times vibration, you've eliminated the possibility of natural frequencies and resonance. You know you're not running your resonance. You trim it out on the top. Okay? You add balance weights to the hub at the top of the motor, on the fan at the top of the motor, and you trim it out. That is a standard procedure for vertical motors. It does not mean that you didn't do your job and the rotor's not balanced. There's other factors come in here when you install it that can generate that 1 times, and you put balance it out, it's gone. That's fine. It'll run smooth. Okay? All right. If you can't balance it out, particularly if it's directional, in line with the discharge, it's running real smooth. Perpendicular is vibrating pretty bad, so you put your transducer on here, put some weights on it, ran a trim balance, got it down. It's running pretty smooth now side to side, and now the vibration is higher in this direction. The problem's not balance. The problem's not balance, because balance is going to be all the way around. You have a directional force probably in the coupling or a shaft that's whipping, okay, but it's probably in the coupling, okay? Likely an alignment problem. All right. Then you need to verify the head and flow if there's motor current problems. That gets back to the pump curve. That's just a little bit of information. And measure something called wire-to-water efficiency. The wire is the volts and amps and three-phase and the power factor of the motor. That's your power in. Your power out is head times flow divided by 3960. Okay? You don't need the efficiency because that's what we're measuring. Power out divided by power in is efficiency. How much water am I getting out for the electricity that I put in? That's a good number to have. You should know that number. Your customer should know that number and what it should be. Okay? So you document that. All right? So mechanically, they're more complex. Vertical motors are more complex, particularly in that bearing in the top, with all the different types of bearings that can be in there. Alignment is a problem. They're just not designed for alignment. Those motors are made to be set on top of a perfectly true motor flange, and you don't have that. They're not made to be adjusted. So that's a problem that needs to be dealt with. You got the problem that you can't turn the pump shaft unless it's already hooked up to the motor. And you got this problem with natural resonance, or natural frequency and resonance, which is always going to be there. Okay? And in some cases, the motor current, when it's an open-style impeller, semi-open, the motor current depends on the amount of clearance at the bottom. Okay? And if you repaired the motor and there's a problem, it must be the motor, right? The problem could be the pump. The problem could be the structure. The problem could be the head and flow on the pump. But, oh, no, you fixed the motor. It's got to be a motor problem, right? Okay. If you follow these steps and if you take these thoughts into advisement and you plan so that when you get to that point where there's a problem, you've got all the data that you need, okay? And don't go into the, well, I could have, well, I would have, well, I should have, okay? And you don't have the data, and then the customer's got a hold of you, and you got problems, okay? So that's what this presentation was about, was trying to get you in a situation or present to you what you should do to get yourself in a position to work with your customer when problems do occur, okay? Sorry I ran over so much. I really apologize. Thank you. Enjoy the rest of your convention, and go see the vendors and tell them we love them.